So when we're looking at logarithmic relationships, the most common use for logarithms is going to be in waves. So we can talk about sound waves, we can talk about ocean waves, or we can talk about shock waves. And a shock wave is like from an earthquake. So this first example is an earthquake example. This is where you would see logarithms in real life being used. The Richter scale is used for measuring the magnitude of an earthquake. The magnitude m, all right, so the magnitude, the value m, is related to the released energy in joules. So released energy is going to be the E by this equation. How much energy was released by the Great San Francisco earthquake of 1906? So it was a real earthquake, burned down a lot of the city of San Francisco because they had a big fire. Measured 8.2 on the Richter scale. So how much energy was that in joules? So the way we do this is we have to plug in for m. We'll plug in an 8.2. All right. And then once I have that plugged in, now I can go ahead and put that into my calculator and I can simplify this left-hand side. So for example, 1.5 times 8.2, and then I add 4.4. That comes out to 16.7. And I get log of E equals 16.7. If I want to algebraically solve this, I'm going to need to change forms. Just like what we did before. So I could do like a base 10 of both sides because it's log base 10 there. And I can get 10 log of E equals 10 to the 16.7. And that really just becomes E equals 10 to the 16.7. And then if I put that in my calculator, all my calculator is going to do is change this to scientific notation. It's going to change it to 5.01 times 10 to the 16th power. And then we'll say J for joules. So in the Great San Francisco earthquake, it turns out that the energy released was 5.01 times 10 to the 16th joules of energy. Which, if you don't understand what a joule is, I'm not very good with joules. So I don't really understand exactly. I can't fathom how much energy that is, but I know it's a lot of energy.
Is there a reason we didn't round up with the 0.7?
Is there a reason we didn't what?
Is there a reason we didn't round up?
For the 0.7?
Yeah.
No, I mean, was it 0.76 or something when we did it on our calculator?
Something like that.
Okay, yeah, I don't know. Let's see, 8.2 times 1.5 plus 4.4. No, I just got 16.7 when I put it in my calculator. So that's the only reason I had it. So I didn't want to round it to the nearest whole number. I just left it at 16.7.
I was talking more like at the very end, like the thing you boxed. Is there a reason that the 0.7 went away?
Oh, so because if you do 10 to the 16.7 in your calculator, it's going to rewrite it in scientific notation.
Okay.
That's all.
Sorry about that. Thank you.
Oh, no problem. And that's when we got the 5.01 e to the 16. That's 5.01 times 10 to the 16th power. That's how we'd rewrite it in scientific notation to be appropriate. Okay. All right, so now problem B says the Richter scale is often misunderstood. In most cases, this is a result of having little or no understanding of the logarithmic nature of the scale. For example, what does the difference of magnitude of 1 make in the released energy? So the idea for part B is to think like, what happens if we have a magnitude 5 earthquake versus a magnitude 6 earthquake? What's the difference in energy? Or we could say a magnitude 4 earthquake versus a magnitude 5 earthquake. That's what I mean when I say a difference of a magnitude of 1. Okay? So like, let's go ahead and look at we'll make one up. Let's look at a 4.0 magnitude earthquake, which in Northern California, you could get one of those every couple of years. All right, that's not uncommon down there. So you go ahead and plug in 4 here, 4.4 plus 1.5 times 4. And then over here you could do maybe a 5.0 magnitude. And we'll compare the difference in strength of these two earthquakes. So the one on the left, the 4.0, 1.5 times 4 is 6 plus 4.4 is 10.4. The one on the right, 1.5 times 5 is 7.5 plus 4.4 is 11.9. Now when I change forms, I'm going to get E equals 10 to the 10.4 power on the left side. And on the right equation, I'm going to get E equals 10 to the 11.9. Again, all I'm doing right now is just trying to figure out what the differences between two earthquakes in terms of power. How much stronger is one than the other? So I've got two different answers here. E equals 10 to the 10.4. I can turn that into scientific notation if I want. But for these purposes, I can just leave it as these two numbers right here. And I can say, let's go ahead and compare them now. And the way we compare is we can say the energy of a 5.0 earthquake divided by the energy of a 4.0 earthquake is going to give us a good comparison. So the 5.0 was 10 to the 11.9 power. And the 4.0 was 10 to the 10.4 power. All we're doing is we're just creating a ratio to say what's the difference in strength of these two. And now I can go and put them in my calculator. 10 to the 11.9 power divided by 10 to the 10.4 power. And I come up with a number, 31.622. Okay. And then the real question is, what does that mean? The 31.622? That means the magnitude 5.0 earthquake is 31 times stronger than the 4.0 earthquake. So that just gives you an idea of the Richter scale. So when you hear an earthquake is 4.0 or an earthquake is 5.0 or 6.0, all right, 31 times stronger when you go up one magnitude for an earthquake. All right, so the Great San Francisco earthquake of 1906 was an 8.2, so that means a 6.0 is going to be 31 times stronger than a 5.0, a 7.0 is going to be another 31 times stronger than a 6.0, and then an 8.0 is going to be 31 times stronger than that. So that's a very, very strong earthquake, that 8.2 in 1906. All right, one of the strongest earthquakes ever recorded, I should say. All right, so that's one example of logarithms being used. All right, it's to talk about wavelengths. So you can talk about sound waves as well, like if you're into music, and you have like a bass box. Okay, you can, if you turn up the bass, it's going to change the frequency of the sound waves. All right, that type of stuff is all using logarithms actually. Okay. Anyway, next, number 2 here says the apparent magnitude of a star is a measure of the brightness of a star as it appears to observers on Earth. So this is a different type of magnitude. The apparent magnitude m of the dimmest star that can be seen is given by this function, where the diameter is the diameter in millimeters of the telescope's objective lens. So if we're looking through a telescope at a star and we measure it in millimeters, that can tell us the brightness of the star. All right. So for this one, it says, hey, we found a apparent magnitude of 12. So what's the diameter then? So we'd kind of be working backwards here. D stands for diameter. So we'd want to solve for this problem. So if the apparent magnitude is 12, we start by first subtracting 2 from both sides. And we get 10 equals 5 times log of d. Then we divide both sides by 5. And we get 2 equals log of d. And now we have to change forms. Or I could say let's do base 10 of both sides. Hopefully this is coming back to you from what we did in before the break. 10 squared equals 10 log of d to the log d power. So we end up getting d equals 10 squared, or d equals 100 millimeters. Which means we put it back in a real life context for this problem. Says that the star is measured at 100 millimeters in diameter when viewed through the lens. That's how these types of problems work, is at the very end we want to think about how does this relate to the real world context of the problem. So if you're into astronomy or anything, stars, anything like that, you could use logarithms in your career. So that's just another example. All right, work for NASA, something like that. Okay. And then the last one here uses Newton's law of cooling. So Isaac Newton used exponentials and logarithms. This is actually an exponential equation. It does for a cooling substance with initial temperature. So whenever we see T naught, it's called T naught, even though it's got a little 0 down there. That always refers to the initial temperature or the starting value. So if we're in chemistry or physics, we're going to see that value a lot, where we see the initial number. All right, it's like a little t with a 0, saying that's what we're starting at time 0, basically. So this one's a little confusing because the temperature is capital T, and then lowercase t happens to be time. So after t minutes. So this one says, if you're driving on a hot day when your car overheats and stops running, it overheats at 280 degrees Fahrenheit. So that's your starting value. Okay, my engine is 280 degrees right now. The car is overheating. And I can't drive it again until I get to a final temperature of 230 degrees. And then I gave you a value here. It just says, hey, if R is 0.0048, we're going to plug it in up here into the exponent, and it's 80 degrees outside, how long do you have to wait until you can continue driving? All right, so 80 degrees outside. So we're trying to solve for t here. So we're trying to solve for lowercase t. How long do I have to wait before I can start driving again? So our final temperature was 230 degrees. And we know our initial temperature was 280 degrees. The car just overheated. All right. And we know T sub R, that's where the temperature outside is. So that's 80 degrees. Okay, and then we say times E to the negative 0.0048 times T plus 80. And then we'd have to algebraically solve for this entire problem. So I would start by, let's say, subtract 80 from both sides. I get 150 equals, I'll do that parentheses, 280 minus 80 is 200. And next, I can go ahead and divide both sides by 200. 150 divided by 200 actually happens to be 3/4. And so it looks like a really intimidating problem at first, I'd say. But now it's not too bad once I have it set up. Because now I just have an E on both sides and I say, okay, I can take a natural log of both sides of the equation. Natural log of 3/4 equals natural log of E to this weird number thing. And the E goes away, the natural log in E goes away, and I can just put natural log of 3/4 into my calculator, and I can divide both sides by this negative 0.0048. I don't have my calculator on me right now, so I'm just going to put that like that. And then we can go ahead and put it into a calculator. I have my answer written down already, but I don't have my calculator with me currently. But I got 59.9, which means it will take about 60 minutes, essentially an hour, before I can drive again. So I guess for this problem, the moral of the story is if you're driving somewhere and your car overheats and you have cell service, you could either call a tow truck or you can just Google this really cool equation and then figure out what your temperatures are and figure out how long you have to wait. Or you can call a tow truck. So, you know, your choice, whichever one makes more sense to you. Anyway, so that's a real world example for this particular problem here. Any questions on this last problem?